Look closely at this tissue. Cells, packed so tightly they're touching. The job, label every pixel as cell or background, and trace the exact border between one cell and the next. Here's the catch. You don't get thousands of labeled examples. You get about 30. In 2015, one network solved this in a single pass, and its shape was, quite literally, the letter U. How did people do this before? One pixel at a time. Take a small patch around a pixel, feed it to a convolutional network, and ask, what's at the center, cell or background, then slide over by one pixel, and repeat. For a 512 by 512 image, that's over 260,000 forward passes for one picture. And the patches overlap almost completely, so you redo the same work again and again. There's a deeper tension too. A large patch sees lots of context, but gets vague about location. A small patch pins down location, but goes blind to the big picture. Context or precision. You seem to have to choose. Here's a smarter idea. Instead of one patch at a time, push the whole image through at once. Convolutions slide across everything in parallel, labeling every pixel together in one fast pass. And to make sense of the image, the network pools information, shrinking the picture so each step sees more. This is the encoder. It figures out what is in the image, and it works. But look what pooling did. Every time we shrink, we lose fine detail. So when we ask where exactly the boundary is, the answer comes back coarse and blocky. The what is right. The where got smeared away. Now, this looks like a flaw. It's actually the key. Think about what lives where. The shallow layers, near the input, still have sharp, precise location, but little meaning. The deep layers, further in, are rich with meaning. They know cell from membrane, but their location is coarse. Sharp location, no meaning. Deep meaning, no location. Each half holds exactly what the other is missing. So what if you didn't choose? What if you connected them? This is UNet. On the left, the contracting path, the encoder, convolve, pool, go deeper, building meaning. On the right, its mirror image, the expanding path, upsampling step by step, growing the picture back to full size. And here's the idea that ties it together. At every level, a skip connection copies the sharp feature maps from the left and hands them straight across to the right. So the decoder gets both deep meaning from below and precise location from across. That handshake is why it's shaped like a U. But architecture alone isn't enough with only 30 images. So they added 2 tricks. First, elastic deformation. Warp each image with a smooth random distortion, so one image becomes an endless supply. Second, a weighted loss. Draw a thin line right where 2 cells touch, and make getting that seam right matter more. High penalty, exactly on the border. Deep meaning, plus precise location, at full resolution. Did it actually work? On the electron microscopy segmentation challenge, UNet took first place, beating the sliding window method it replaced. On the 2015 cell tracking challenge, it won 2 datasets by a clear margin, with overlap scores around 92% and 78%. And it was fast, a 512 image, segmented in a fraction of a second. The lesson wasn't a bigger model, and it wasn't more data. It was a shape that refuses to throw away where things are. That one shape, an encoder, a decoder, and skip connections between them, became one of the most reused designs in all of deep learning. Cell biology, satellite and road maps, medical scans, even the image generators behind modern AI. So, one question to leave you with. What else could you solve just by refusing to forget where things are?